I'm happy to begin today's session. Thank you. My name is Alexander Denisenko, and I represent Sberdevices. It is a unit of Sberbank, the biggest bank in Russia and Eastern Europe. My colleagues, Nikolai Karpov and Fedor Minkin, couldn't make it to Brno this year, so I'll be presenting our work on my own. Sberdevices specialize on developing smart devices and everything that comes with it. I am a member of speech recognition team, and almost everything I do revolves around data. I'm going to tell you about GOLOS, a Russian dataset for speech research, which we have recently created and made open for free public usage. Creating such datasets was necessary for us in order to have good ASR and TTS systems in our devices that have a voice assistant, in particular a smart screen device called Sber Portal, which is presented on the slide. GOLOS is the first completely manually annotated Russian dataset of such size, and it comes with a license that lets it be used for commercial purposes. We hope that this dataset will be a major step forward for Russian speech recognition systems. The dataset consists of 1,240 hours of audio and more than 1 million utterances. All of them are completely manually annotated, in contrast to most of the big datasets out there. The dataset transcriptions are purely Cyrillic letters and spaces, and the dataset consists of two parts. The first part, which we call crowd, contains audios which were recorded with the crowdsourcing labeling platform called Taloka. The second part, which we call far field, is comprised by audios recorded with our smart screen device, Sber Portal, which was presented on the first slide, using relatively long distances between the speaker and the device. Think of 1, 3, or 5 meters. Here you can see the duration distribution in the training part of our dataset. An average duration for both subsets is somewhere around 4 seconds, and 99% of utterances do not exceed 10 or 11 seconds. We have collected the data using the following pipeline. Let's go through it step by step. In order to create user-alike queries, we've been using a so-called template system. First, we define the domains we are interested in, such as music, films, phone calls, and many more. Then, for each domain, we define certain entities. For example, for music, it would be something like artists, tracks, comments to the assistant, and we fill these entities with data. So we get something like a database for a certain domain. Then we define the rules of how these entities could be combined together so that the result would resemble a possible query from the user. And at last, we generate a lot of text queries based on these rules. Now we have these texts generated from the templates. We also add a lot of open domain questions like, which programming languages do you know? Or who will be the next president of Russia? And we send all these sentences to the crowdsourcing labeling platform and ask people to vocalize them. Then we ask people to transcribe previously vocalized texts. It's important to mention that each audio was transcribed by 3 people. If at least 2 out of 3 transcriptions were the same, we use it as a correct label. Everything was transcribed using Cyrillic letters and spaces. And to ensure the quality of labeling, we've been using the so-called honeypots. When among the data to be labeled, we put some samples to which we already know the answer, correct labels. And when somebody shows poor form on these honeypots, we ban the person and relabel all the samples this person has already transcribed. However, if we try to transcribe an audio which contains foreign words using the usual transcription process, we see that the consensus of labelers on the crowdsourcing platform is significantly lower than when we transcribe the audios which contain Russian words only, as all of the labelers speak Russian and not that much can speak and hear in nice English. And this especially is a problem when we speak of something like music domain, where the titles and the names can be quite confusing. Therefore, for such situations, we've been using a different process, which turned out to be very helpful. At first, we asked 5 labelers whether the original text that was vocalized matches the audio, to throw away some badly vocalized samples. If at least one person said that the audio doesn't match the text, we throw the sample away. And if it does match the text, we then ask the labelers to transcribe the audio in Cyrillic letters, while also showing them the original text, which might contain English letters, diacritical symbols, and everything else. One sample is presented to 5 labelers, and if the most popular transcription was written by at least 2 labelers, we consider it to be a correct one. Both these steps are conducted with previously mentioned honeypot system to ensure the quality of labeling. In order to validate our dataset, we performed several experiments. Speaking of acoustic model, and we've been using QuartzNet 15x5 model, we train it using either just our dataset or with additional smaller Russian part of Common Voice dataset. We train it either from scratch or use the model that we've pre-trained on English language. For the language model, we use an n-gram language model with the help of KennelM toolkit. When it comes to language model experiments, we create the language model based on the trained part of Golos dataset or on the common crawl dataset, or we combine both. On this picture, you can see the effect of pre-training on English language, as well as the difference between 10 and 20 thousandths of steps. It turns out that the model that was pre-trained on English language is much more accurate than the one that was trained from scratch. And here you can see the quantitative results achieved by acoustic model using greedy decoder without any language model at all. Well, it turns out, just as usual, the longer you train, the better you perform, but at some point the profit is kind of diminishing. For example, our best model is a model trained for 50,000 steps, which was pre-trained on English before, but it took us 8 days to train the model on Russian dataset. To achieve this quality, 8 days on 16 Tesla V100 GPUs. So we decided to stop at this point. And on this slide, you can see the improvements made when training on Golos and Common Voice datasets with an added n-gram language model. The first line shows the results with the greedy decoder. On the second line, you can see the results when the language model used is the one built on a common crawl dataset, which represents the data crawled on the web. It is more general and all-encompassing, but it contains all sorts of strange things and typos, just as the internet does. The third line shows the results when the language model is built solely on the trained part of Golos dataset. And on the last line, you see a language model. You see the results obtained with language model, which was a mixture of language models built on Common Crawl and voice and Golos datasets. So as a conclusion, we've gathered and made public a dataset called Golos, which is the first big manually annotated Russian speech corpus. It contains more than 1,000 hours of speech and more than 1 million utterances. We've trained a QuartzNet acoustic model on Golos and created several variations of language models with additional part of Common Crawl dataset, and with it, we've created several language models. All of these language models and the acoustic model and the dataset itself is available on our GitHub, github.com/beardevices/Golos. It can also be accessed through this QR code. And if you have any questions, I'll be happy to answer them. Thank you.
Thank you very much, Alexander. We have plenty of time for questions. Just a reminder, obviously, if you're in the room, you can just raise your hand and someone will come to you with a microphone. But if you're watching online, you've got the option to ask in the chat, or if you want to be connected live to the room, you can raise your hand and we will try and connect you through. There's 2 questions there.
But I can hear you just fine.
Yeah, okay. I was just wondering, for collective languages as Russian, did you try, it might work better if you tried like subword units, BPEs. Did you try something to that direction?
If you tried what? I'm sorry?
Subword units as byte pair encoding units or something like
okay.
that.
I mean, the results that we've shown are not the best results that we could have achieved. These are just the results to show the adequacy of the dataset and the general performance. We did not put much effort to achieve the best possible result here. Just an example, but in our work related to the production, no, we did not try such methods as you mentioned.
Have another question at the back.
Hello. I'd like to ask whether are you considering extending the transcripts with further annotations like named entities or like punctuation, true casing, things like that?
You're asking what we do for the punctuations and stuff like that?
No, I'm asking if you're planning to use this data set further to, for example, run another annotation procedure where people would, I don't know, check or verify spans of entities, for example, on running just a Russian spacey model on with the onto node scheme on the transcript, and then showing people just to like correct them, move them, and then have a nice data set with also entities annotated or things like that. Like, are you planning to extend the annotations further after the transcription?
Mm-hmm. If I understood you correctly, you asked whether we are going to extend the transcriptions for this data set further in order to get like some stuff like punctuation and so. Actually, we haven't thought much of that yet. Maybe we'll have hopefully some future additions to the data set, maybe even some new, like even bigger ones. But as of now, we haven't been planning to add some punctuation because for this data set, we don't have such data ourselves. And when it comes to the bigger part of this data set, I have to say that actually there's not much room for useful punctuations here, as most of the queries, most of the text, most of the utterances, they are simple and relatively simple and quite short sentences. You won't find any long sentences from the textbooks here. No, it's mostly some questions and text regarding the domains like films, music, food delivery, some ODQA. So it's like it's not like some datasets that are comprised of huge sentences from the books. So I guess it wouldn't be that useful as in these cases. Yeah.
Hi, I have another question. So thanks for the very clear talk and interesting work. Can you tell something more about the data? Like how many different speakers there are and what kind of metadata you can share?
Speaking of metadata, I guess we can't share any, but speaking about number of speakers, this is likely somewhere between thousands and tens of thousands of speakers, because this labeling platform, crowdsourcing labeling platform Toloka, which is popular in Russia, it has quite a lot of labelers, quite a lot of performers there, and they are all Russian people or Ukrainian and Belarusian, and they speak fluent Russian language. So in terms of diversity, this is a very good data set, I'd say.
Thanks. We still have time for some more questions. There's a comment in the chat from Suzanne Berger. She says, thank you for the talk. And comments that the content of the recordings were answer to the questions. I'm not sure, Suzanne, if that's really a question, but maybe more of a comment. And if anyone else would like to raise their hand virtually or physically.
I have a question. So, what's the coverage of the vocabulary? Means in the paper I read, I didn't get an idea like how many number of words, unique words you have in this.
Yeah,
and from this you're creating a language model and so on, right? So, can you give an idea about that?
I don't recall exactly, but the best performance was achieved when we were mixing the language model that was built on our data and the data from Common Crawl dataset. And Common Crawl dataset is the one that was obtained from crawling the web. So in terms of Russian words and some slang maybe, almost everything is in there. So these are like tens of millions, like many of them are wrong. As you can understand, when crawling the web, there are a lot of typos, and that has been sometimes a problem for us because we need to distinguish between good, really existing words and some trash. And actually, when it comes to the vocabulary, a problem that we are solving right now is that our model predicts Cyrillic symbols and can predict Cyrillic symbols in spaces. But our language model also has some English words, some French, some German from music and other domains. And if we want to predict, for example, if somebody asks, can I listen to Linkin Park in the end, we need to understand how to predict Linkin Park in the end. So we've built an extensive base of so-called mappings between the Cyrillic symbols and all the other languages. So this has been like a problem to which we have found the solutions for ourselves in terms of vocabulary. But speaking of Russian, everything is in there, yeah.
Yeah, but another thing I'm asking is like in your collected data, what is the vocabulary coverage? Like how many unique words did you find in the collected data?
If you're interested, I can answer you afterwards.
Okay.
But right now, I don't recall actually.
Okay. Anyone? I have some more questions.
There's another question in the chat, actually. This is from Mel Huber, who says, are you going to maybe introduce some noises in other versions of the data set? Some noise.
You mean if it's possible to release the data set where there would be some background noise? Like, I guess if we are going to have some future iterations, which I hope we do, then it is possible to do this because all the data which we got from this labeling platform, it was recorded using mobile phones. So we can put the task, we can make the task this way so that the labeler, so that the performers would go to some noisy places and record it there and then validate it afterwards. So technically, it's quite convenient to do it, and we'll make sure that in the further iterations we'll include these queries. Yeah, thank you.
Thanks very much. I think we can move on to the next speaker now. So let's just thank Alexander again for his presentation.
Thank you.